Most people walk past the easiest clue that a diamond might be fake: the luster. Under ordinary light, genuine diamonds emit a fierce, metallic gleam known as adamantine luster. It's not the sparkle that tricks most eyes, it's the nature of that sparkle. Fakes like glass or cubic zirconia reflect more diffuse, oily light that may dazzle but doesn't cut sharply across facets. It's this difference in how the light exits the surface, crisp versus smeared, that trained gem testers pick up immediately, even before any tools come out. The problem is, a casual glance isn't enough. The surface finish of fakes has improved dramatically, and unless the stone is dirty or chipped, it can seem convincing at first. But there's a practical field test that uses nothing more than sunlight and a bit of patience. Hold the stone under strong directional light and rotate it slowly. If the facet edges flash with harsh, lightning-like brilliance and go instantly dark at angle shifts, you're likely dealing with a diamond. If instead the light spreads like a soap bubble, or the whole stone glows evenly with soft hues, it's almost certainly not. This test works on cut stones and even well-shaped rough. In fact, rough diamonds often show a greasy, matte exterior until cleaned, but once polished or broken, that hard-edge gleam returns. The key is the lack of glow. A real diamond looks like it's slicing light, not glowing from within. Still, this is only a first pass. Some high-index fakes like moissanite or yttrium aluminum garnet, YG, can imitate adamantine luster well enough to confuse even experienced handlers. That's when physical feel, weight, temperature, and friction starts to matter more. Because while sparkle catches attention, heft reveals deception. And that's where the next test comes in. The moment a stone is lifted, trained hands can register a lie. Density, the weight in hand, is one of the fastest and least appreciated ways to filter out fakes. Genuine diamond feels light for its size, a subtle but consistent trait once you've handled a few. Most convincing substitutes, especially cubic zirconia and synthetic spinel, are simply too heavy. Cubic zirconia's specific gravity, around 5.6 to 6.0, makes it feel dense and overbuilt when compared to diamond's 3.52. That gap isn't trivial, it's tactile. Field gemologists often carry a small control stone, like a flawed natural diamond or clear quartz crystal, for direct comparison. Two similarly sized stones in the hand, weighed by intuition alone, will often sort themselves. When holding a 5 mm round stone, about 0.5 carats in diamond, any noticeable heft beyond expectation is suspicious. If it feels oddly weighty, especially relative to its apparent volume, you're probably not holding carbon. There's a compounding clue here. Heavier simulants tend to be softer as well. Cubic zirconia ranks about 8.25 on the Mohs scale versus diamond's perfect 10. That means if a stone feels heavy and has minor surface abrasions visible under magnification, the odds swing sharply against it being real. Glass, even cheaper than zirconia, often fails both the weight and hardness checks simultaneously, chipping easily and feeling inert in the hand. Another test that relies on density is the splash test. Drop the stone gently into a small glass of water. Diamonds, being less dense than CZ, sink slower than one might expect. Fakes hit the bottom quickly and without hesitation. It's not diagnostic on its own, but when paired with weight intuition, it adds confidence. These physical traits aren't just curiosities, they're exploitable patterns. Many fraudulent sellers count on visual distraction to override tactile instinct. But gem buyers and field testers who've held enough real stones know what balance feels like. The density mismatch becomes a fingerprint of deception, and once noticed, is hard to forget. Still, weight alone can't distinguish a diamond from moissanite, which shares a similar density range. That's why we layer tests. Weight tells us something's wrong, but not yet what. For that, we turn to something even simpler: magnetism. Not all fakes are inert, and some betray their origin with a flick of iron. Few expect a diamond test to start with a refrigerator magnet, but it's one of the fastest ways to disqualify certain imposters. Many high-density synthetic stones, especially those produced for industrial uses, contain trace amounts of iron or other magnetic elements that shouldn't be anywhere near natural gem-grade material. While diamond itself is completely non-magnetic, several common substitutes, particularly certain spinels and heavy lead glass composites, show a faint but detectable attraction to a strong neodymium magnet. The field version of this test is simple. Lay the suspect stone on a flat, stable surface, preferably glass or polished stone to reduce friction. Pass a rare earth magnet slowly within a centimeter of the stone's edge. If the stone shifts, slides, or reacts even subtly, it's not a diamond. You've just uncovered either a synthetic with magnetic inclusions or a composite designed for visual mimicry, but structurally flawed. Industrial-grade cubic zirconia, for example, sometimes includes yttrium or iron stabilizers, especially in older batches, making it weakly magnetic. For small stones, this test may require an enclosure. A folded paper or plastic card helps reduce wind disturbance and finger error. Suspended versions of the test, where the stone hangs on a fine thread, can improve sensitivity, but are harder to perform in the field. Still, even a minor shift on a flat plate under magnetic influence should raise immediate doubts. This isn't a catch-all. Moissanite, the top-tier synthetic rival to diamond, is also non-magnetic, as are most high-end cubic zirconia cuts designed for jewelry. But the value of the magnet sweep lies in its elimination power. It costs nothing, risks nothing, and rules out an entire class of deceptive materials in under 10 seconds. No damage, no scratching, no chemicals. It also highlights an often overlooked truth. Many fake diamonds aren't even made for jewelry. They're repurposed industrial crystals, synthetic remnants, or composites, shaped, polished, and set in deceptive mounts. Their performance under visual tests might be strong, but their physics betray them. When exposed to long-wave ultraviolet light, some diamonds emit a distinct glow, most commonly blue, though shades of white, yellow, or even orange can appear. This reaction, known as fluorescence, is due to trace elements like boron or nitrogen in the crystal lattice. Under the right conditions, it can help confirm a diamond's authenticity. But fluorescence is one of the most misused and misunderstood signals in field gemology. Roughly 25 to 30% of natural diamonds exhibit some level of fluorescence under UV. That means the majority, perhaps surprisingly, do not. So while a blue glow under long-wave UV might align with a natural diamond's profile, its absence doesn't disprove authenticity. And the presence of fluorescence alone isn't proof either. Several simulants, including synthetic spinel and moissanite, can also fluoresce, sometimes even more brightly. The difference lies in character. Genuine diamond fluorescence is typically subtle, distributed evenly across the stone, and often has a soft, chalky texture under UV. Moissanite, on the other hand, may fluoresce more intensely and unevenly, with a bluish-white tone that seems too loud. Synthetic spinels often glow orange or red, instantly disqualifying under the diamond profile. Some cubic zirconia glows pale yellow, especially under short-wave UV. Another clue worth noting: there's also a market layer to this trait. In high-end diamonds, strong fluorescence can sometimes reduce resale value, especially in colorless grades where the blue glow alters perceived clarity in daylight. Yet in near-colorless or faintly yellow stones, moderate fluorescence can make the diamond appear whiter. That visual compensation can, paradoxically, increase appeal if it's natural. In field testing, a compact long-wave UV flashlight can be a powerful tool for quick sorting. A stone that fluoresces orange, green, or red under LWUV Almost certainly not a diamond. One that glows intense white blue? Possible, but warrants further scrutiny. And one that remains dark while others light up? Not disqualified. Just moving on to the next step. Because fluorescence, while fascinating, isn't definitive. It can eliminate bad candidates and hint toward promising ones, but it can't stand alone. For that, we go closer into the micro-world of facet junctions, polish quality, and the optic quirks that only a loupe can expose. Magnification is where illusions start to crumble. A 10x loupe, standard in gemology, reveals fine structural differences that no naked eye can detect. The most telling of these, when verifying a diamond, are the sharpness of facet edges and the presence or absence of optical doubling. While surface luster and fluorescence offer broad signals, the loupe shows how light actually behaves within the stone's geometry. Start with facet edges. On a genuine diamond, these junctions are razor-sharp, clean, intersecting lines that meet with almost mathematical precision. Even under 10x magnification, they retain crispness with little to no rounding. In contrast, most fakes, especially glass, zircon, or low-quality cubic zirconia, display soft or melted edges. These are the result of polishing limitations and the lower hardness of simulants, which cannot maintain the same keenness during cutting. Then comes optical doubling, a phenomenon where internal features, such as facet lines or inclusions, appear doubled when viewed through the crown or pavilion. This is a key test for moissanite, the most convincing diamond simulant on the market. Because moissanite is doubly refractive, light entering the stone splits into two paths, making internal features look blurry or doubled under magnification. Diamond, being singly refractive, does not exhibit this trait. So, if you observe a duplicated girdle reflection or internal structure, especially through the table at an angle, you're likely not looking at diamond. It's critical to control lighting during this inspection. Use daylight equivalent LED or fiber optic light to minimize glare. Tilt the stone slowly under the loupe and watch how internal lines behave. If a single girdle line splits or appears wavy, the optical clarity is compromised, usually a moissanite giveaway. Even some high-quality synthetics like yttrium aluminum garnet, YG, may show internal strain patterns or anomalous birefringence under polarized light, further aiding identification. Inclusions themselves aren't disqualifying. In fact, most natural diamonds have some internal features, pinpoints, feathers, or tiny crystals. The key is their nature. Natural inclusions are typically irregular and scattered. Fakes may show bubbles, swirls, or layered structures, especially in glass composites or flame-fused stones. This is where gemology moves from guesswork to geometry. The loupe doesn't just magnify. It reveals how light travels, how edges endure, and how flaws arrange themselves. But even this test has limits. Moissanite's doubling can be subtle, and flawless lab-grown diamonds can fool all but trained eyes. That's why the next stage demands a shift in physics, not optics. Diamonds don't just shine differently. They conduct heat differently. And it's this property, tested with a small handheld probe, that offers one of the clearest separations yet. When light and weight fail to settle the question, heat steps in as the deciding force. Diamond is among the most thermally conductive materials known to science. More than copper, more than silver. This trait makes it ideal for industrial applications and, critically, nearly impossible to fake in jewelry without leaving a thermal fingerprint. That's where the thermal conductivity tester earns its reputation. It offers the first decisive yes or no in many gem identification workflows. A thermal probe measures how quickly heat transfers from its tip through the stone. When touched to a diamond, the probe's temperature drops rapidly, triggering an audible or visual confirmation on most devices. This effect is unmistakable. No other commonly available gemstone responds with the same speed. Glass, quartz, cubic zirconia. They all absorb heat sluggishly by comparison and fail the test outright. However, this is only a first-tier confirmation for one reason: moissanite. Engineered to closely mimic diamond's thermal behavior, moissanite often passes thermal tests, particularly with older or low-sensitivity devices. That means a positive result doesn't prove authenticity. It only narrows the field. What it does do, however, is eliminate dozens of low-value pretenders in seconds. Proper technique is essential. The probe must make firm contact with a flat, clean facet, usually on the table of the stone. Oils, dirt, or curved surfaces can cause false negatives. It's also important that the stone be stabilized. Loose settings or small melee diamonds may shift under the probe, disrupting the reading. For best results, use a freshly charged or calibrated tester, and allow both the stone and probe to reach room temperature before beginning. Some testers now include dual-mode functionality, switching automatically between thermal and electrical conductivity tests to address moissanite interference. A critical upgrade, as we'll explore next. But even with basic models, thermal testing filters out most simulants and validates further investment in verification. The real strength of this method isn't just speed, it's pattern breaking. When a stone passes luster, density, and thermal in sequence, the odds of authenticity rise sharply. It tells a coherent story, one that moissanite still tries to sneak into. To stop that last deception, we turn to the one test moissanite almost always fails: electrical conductivity. Because diamond may carry light, but it doesn't carry current. Moissanite has fooled thousands by mimicking diamond's sparkle, weight, and thermal response, but it carries a hidden flaw. It conducts electricity. Diamond does not. This fundamental difference in electrical behavior allows gem testers to expose even the most convincing thermal impostors using a conductivity probe. If thermal testing is the sword, electrical testing is the scalpel. It narrows the field to the truth with cold precision. The principle is simple. Electrical conductivity testers send a low-voltage current into the stone and measure how easily electrons flow through it. Moissanite, made of silicon carbide, permits current to pass. Diamond, composed of pure carbon in a tetrahedral lattice, is an electrical insulator. Even synthetic diamonds, unless doped with certain elements for industrial use, remain non-conductive. That means a stone that registers positive under thermal and conductive testing is almost certainly moissanite. Field versions of this test are increasingly compact. Devices like the Presidium Duo or multi-mode gem testers now combine thermal and electrical probes into one unit. The workflow is sequential. First confirm thermal response, then check for conductivity. A stone that passes thermal but also conducts electricity can be confidently disqualified from diamond status. It's the final strike in a layered testing strategy. Still, false positives can occur if the stone is dirty, moist, or held with bare fingers. Conductive oils from the skin or residue on the table facet may transfer current and skew results. That's why proper contact is essential. Always clean the stone with alcohol or lens cloth, and use insulated tweezers or gloves. Ensure the probe tip makes contact with a flat surface. No girdles or prongs interfering. There are rare edge cases. Certain fancy-colored diamonds, especially blue diamonds with boron impurities, can show weak electrical conductivity. But these stones are exceptionally rare and usually accompanied by a host of other traits, e.g. color zoning, visible inclusions, or known origin. In nearly all jewelry and field contexts, conductivity equals moissanite or synthetic. This test finally bridges what thermal alone cannot. Together, they carve a clear path. A stone that's light, brilliant, thermally conductive, but electrically inert checks every box for diamond. Anything else, especially electrical response, ends the inquiry. But there's still value in simple low-tech cues. because even breath, under the right conditions, can reveal what electronics might miss. In an age of precision probes and advanced diagnostics, it's surprising how often breath reveals the truth. The fog test, using nothing but your breath on the stone surface, is one of the most accessible, non-invasive ways to distinguish real diamonds from fakes. And it works because of diamonds' superior thermal conductivity, the very trait explored with instruments, but now applied in the simplest possible way. Here's how it works. Breathe directly onto the stone's flat surface, ideally the table facet, just as you would fog up a mirror. Then observe. A real diamond will dissipate that moisture almost instantly, within 1 to 2 seconds, due to its rapid heat dispersion. The surface will clear before you've finished blinking. By contrast, a fake stone, especially glass, cubic zirconia, or quartz, will hold that fog for several seconds longer, sometimes 5 to 7 seconds, due to their poor heat conductivity. The reason is physics. When you exhale warm, humid air hits the cooler stone, condensing into a visible fog. In a diamond, the heat quickly moves away from the surface, equalizing temperature and evaporating the condensation rapidly. Simulants lack this internal thermal pathway, so the moisture lingers. To run the test properly, clean the stone first. Residue can trap moisture and obscure results. Perform the test in a dry, room temperature environment, avoiding areas with high humidity. And make sure to compare results with a known control if possible. Even small differences in clearing time can point decisively toward authenticity. There are caveats. This test loses accuracy on very small stones or mounted pieces where airflow is restricted. It also doesn't differentiate moissanite, which clears fog almost as quickly as diamond due to its similar thermal profile. But when used in sequence, after a stone has passed basic luster and weight checks, the fog test reinforces the case for or against diamond in seconds. Its real value lies in accessibility. No tools, no damage, no cost. A vendor in a market, a collector in the field, or a buyer in a pawn shop. All can deploy this in moments. And when results are unclear, it prompts a deeper look. Because if a stone fails the fog test, it rarely passes the next one. Sometimes the smallest actions yield the clearest answers. The water drop test, placing a single droplet onto the table of a stone, can expose surface energy and polish characteristics that no sparkle alone can confirm. It works on the same principle that makes wax repel water and glass hold it. Surface tension. And diamond, thanks to its tight crystal lattice and exceptional polish, reacts very differently from impostors. Here's the method. Place the stone table up on a stable surface. Using a dropper, pen tip, or even the end of a moist toothpick, carefully deposit one small droplet of water onto the flat surface. Now observe. On a real diamond, the droplet will bead tightly, forming a high, domed shape with clear edges. It sits almost like a miniature ball, compact, cohesive, and well-rounded. This is due to the stone's low wettability and high surface energy. Fake stones, especially glass and cubic zirconia, tend to flatten the droplet. The water spreads wider, losing height and cohesion. On these materials, the surface tension isn't strong enough to maintain a clean dome. You may also see the droplet creep across the facet junctions or break apart if the surface is imperfectly polished. Another red flag. It's a subtle test, best used in controlled light and on well-cleaned stones. Finger oils, dirt, or humidity can interfere, so wipe the surface clean with alcohol or a lint-free cloth first. For even clearer contrast, run the test side by side with a known diamond. The difference in droplet behavior, beaded versus spread, is often immediately apparent. What makes this test valuable isn't just its simplicity. It's the way it adds nuance to the surface inspection. A fake stone that looked brilliant under normal light, but flattens a droplet may be hiding polishing flaws or surface treatments. Some glass-based fakes are coated with thin films to enhance brilliance. But these coatings alter surface energy and often fail the water test spectacularly. Moissanite can sometimes mimic the beading behavior of diamond, especially when finely polished. But even here, under magnification, the droplet may show tiny irregularities or edge pull, exposing the slight difference in polish chemistry. Together with the fog test, this surface tension trick gives you a paired set of tools for reading polish quality and thermal flow, without any risk to the stone. If both tests lean diamond, you're building a strong case. But to push from likely to confirmed, we now enter the realm of physics and math. When speculation needs numbers, specific gravity settles the argument. It's one of the oldest and most reliable tests in gemology, and it works because every mineral has a distinctive density, measurable through simple water displacement. For diamond, that number is consistently around 3.52. Simulants like cubic zirconia, glass, and quartz fall far outside that range, and even close contenders like moissanite, 3.2 to 3.3, show enough difference to catch with a good scale and steady hands. Here's the field method. First, weigh the stone in air using a precision digital scale, recording the result in carats or grams. Then suspend the stone in water using a thin thread, wire, or a small metal basket, ensuring it is completely submerged but not touching the sides or bottom. Weigh it again. This time, it's measuring apparent weight in water, which is reduced due to buoyant force. The difference between the two weights reveals the volume displaced. Now divide the dry weight by the loss in water weight. The result is the stone's specific gravity. For example, if a stone weighs 1.00 gram in air and 0.72 grams submerged, the loss is 0.28 grams. 1.00 divided by 0.28 is equal to 3.57, a strong candidate for diamond. But if that number comes out closer to 5.6, you're holding cubic zirconia. If it's 2.65, likely quartz. If it's under 2.5, probably glass. The test has margin for error, especially on very small stones. But with care, it can distinguish between diamond and most impostors. The key variables are temperature, water purity, and avoiding air bubbles. Room temperature distilled water gives the most consistent results, and a gentle tap before submersion helps dislodge bubbles that would skew the weight. Specific gravity is especially useful on rough or uncut stones. Visual clues may be ambiguous, and polish tests aren't always applicable. But density is harder to fake. Composite stones may resemble diamond in color and shape, but their internal makeup exposes them when placed on the scale. Even moissanite, the best mimic in most other tests, rarely hits 3.52. It generally measures between 3.20 and 3.25, enough to cast doubt when everything else seems too perfect. And if you're testing a stone that fails gravity outright, say, measuring 4.0 or above, it can be eliminated from consideration as a natural diamond in seconds. At this point, most fakes have been ruled out or strongly flagged. But there's one more optical check worth performing. One that uses flat surfaces and a trick of visibility. Because sometimes, just being able to read through a stone is proof enough that it's not what it claims to be. No diamond should ever behave like a window. This is the premise behind the flat mirror test, a visual experiment that uses one of a diamond's defining optical traits, its extreme refractive index, to distinguish it from fakes. The principle is simple. If you can clearly see letters, lines, or images through the bottom of a stone, it's not a diamond. Here's how it works in practice. Place the stone, table side down, on a piece of newspaper or a page with small printed text. Press it flat so the bottom facet is flush with the paper, and look directly down through the pointed end, the pavilion. If you can make out any readable letters, even blurred ones, the stone is transmitting light too cleanly. That transmission is impossible through a real diamond's complex internal light path. Why? Because diamond's high refractive index, 2.42, bends and scatters light so dramatically that anything directly beneath it becomes distorted beyond recognition. Real diamonds reflect and refract incoming light off multiple internal facets before it exits, creating brilliance and fire, but completely obscuring any image behind it. Simulants like glass, quartz, and some cubic zirconia lack this level of refraction, allowing partial or full readability beneath. The test is especially effective with stones that are flat-bottomed or poorly cut. Like many commercial fakes, a real diamond cut with proper depth will block almost all light passage from below. But even a poorly cut real diamond still scrambles transmitted light. Only low-index materials, often passed off in rings or costume jewelry, permit visible read-through. A variant of this is the dot test. Draw a small black dot on a white sheet of paper and place the stone over it, table side down. Look directly through the top. In fakes, the dot may appear as a clear black spot or even reflect up as a double dot. In a genuine diamond, the light path bends the image to the point of invisibility. The flat mirror test isn't perfect. It won't catch moissanite, which also obscures text due to its similar refractive index. Nor will it work well on very small melee diamonds, where facet angles and curvature distort outcomes. But as a quick screening method for obvious fakes, it's powerful. If you can read through it, you can reject it. The scratch test is often mythologized, shown in movies, whispered in antique shops, and attempted in pawn shops with varying degrees of recklessness. The idea is simple. If a stone can scratch glass, it might be a diamond. But that simplicity masks a dangerous truth. Many stones can scratch glass, and misusing this test can destroy value, both of the suspect gem and anything it's used against. First, the science. Diamond is the hardest naturally occurring material on Earth, ranking 10 on the Mohs scale. Glass sits around 5.5 to 6, and quartz, found in sandpaper and granite, ranks at 7. That means plenty of materials, including moissanite, 9.25, synthetic corundum, 9, and silicon carbide-based fakes can easily scratch glass. So if a stone does scratch glass, it only tells you it's harder than 6, not that it's a diamond. What's more revealing is what the stone cannot be scratched by. A true diamond will resist all attempts by lower Mohs hardness materials. Using silicon carbide sandpaper, Mohs 9, or even a steel file, around 6.5, should have zero effect. However, these tests are risky. Scratching the surface of a gem, even to prove it's real, can introduce microfractures or mar the polish, reducing both beauty and market value. And if you're wrong, you've just defaced a fake with no gain. For small field checks, a better alternative is controlled abrasion using a known Mohs hardness pick set. These tools are designed to test scratch resistance without damaging legitimate stones. Touch the pick gently to an inconspicuous facet, using minimal pressure. If it leaves no trace, the stone is harder than the pick. Work upward in hardness until a mark appears, then stop. You can also test reversibly. Try to scratch a quartz crystal with the mystery stone. If it leaves a sharp, continuous scratch, it's at least harder than 7. That's a positive signal, but still not unique to diamond. On the other hand, if the stone itself scratches or shows drag marks, it's ruled out immediately. Glass, plastic, and most composites fail this test fast. There's also tactile risk. Some fake stones, particularly doublets and triplets, layered materials fused together, can delaminate or chip under pressure. Others are coated with thin optical films to boost brilliance, which can peel or haze under abrasion. So while hardness remains a diagnostic trait, the scratch test is best left to professionals or controlled lab settings. In most cases, conductivity, luster, and density will eliminate the need entirely. But when a stone survives all that scrutiny, its outer shape becomes critical, especially in rough form. Most people wouldn't recognize a rough diamond if it landed at their feet. Unlike the glittering finished gems seen in stores, raw diamonds are often cloudy, oddly shaped, and easily mistaken for quartz or common gravel. But trained eyes know the silent signatures of natural formation, specifically the distinct crystal habits that only diamond shows in uncut form. The most diagnostic of these is the octahedral habit. Diamonds form in the cubic crystal system and, in their natural state, often develop as sharp-edged octahedrons, 8 triangular faces meeting at near-perfect symmetry. These edges aren't soft like quartz or frosted like topaz. They're hard-edged, geometric, and sometimes lightly curved due to resorption in the kimberlite or lamproite matrix. A real rough diamond may appear slightly waxy, even greasy, but the geometry gives it away. Less common, but still valid, are dodecahedral and cubic habits. Dodecahedrons tend to show more rounded faces, often due to partial weathering or chemical etching during ascent from deep mantle origins. Cubic diamonds, rarer still, often have a more blocky, blunt appearance, confusing for the inexperienced collector. Another clue is the lack of cleavage planes in exposed rough. Diamonds have perfect octahedral cleavage, which means when broken, they tend to split along precise, flat planes. If you find a rough stone that's irregular or shows curved fracture lines, it's probably not diamond. But a clean, planar break with near-glassy luster on one face? That demands attention. The texture also matters. Real rough often shows tiny trigons, triangular growth patterns etched into the surface, especially on older, partially resorbed stones. These aren't easy to fake and rarely appear on synthetics or simulants. Under magnification or loupe, trigons look like micropyramids stamped into the face of the crystal, hinting at its slow growth in ultra-high pressure conditions far beneath the Earth's surface. In terms of color, rough diamonds range from clear to milky white, brown, gray, yellow, or even greenish hues. Many industrial-grade diamonds are opaque or deeply included, but gem-grade rough tends to be translucent when wet or backlit. Still, color alone isn't conclusive. Many quartz crystals and topaz nodules show similar shades, but not the geometry or luster. Importantly, real rough diamonds are rarely found just lying on the surface. They're most often liberated from weathered kimberlite pipes, alluvial deposits downstream from erosion zones, or trapped in high-pressure lamproite dikes. Knowing the geology improves your odds, but recognizing the shape and habit is what turns a rock into a find. And yet, even rough with perfect habit can deceive, because lab-grown diamonds, especially HPHD types, also form in octahedra. To tell the natural from the synthetic, internal features and inclusion mapping must be used. But even that assumes you've ruled out everything else.